In this section, we're going to continue talking about Riemann sums and introduce definite integrals. So when we're talking about definite integrals, we are talking about area and signed area under the curve. We talked about signed area in the last section, but in this case, now we're going to give a name to that area, and this is going to be the definite integral. So the signed area from f of x to the x-axis on the interval a to b is given by the integral from a to b f of x dx. This looks just like the indefinite integral from 2 sections ago, except that now we have bounds, this a and b, on the integral. And again, this is known as the definite integral instead of indefinite integral. And from last time, we can say that this is going to be equal to this limit of the Riemann sums. We'll draw some pictures of that to remind ourselves what that means. So first, when we're thinking about signed area, let's think about what that means. So let's just draw a function here. Here is f of x. And if we're thinking from a to b, so we're going to have 2 bounds here, a and b, x values. We're talking about signed area. We're looking at from the function to the x-axis. So when we're below the x-axis, that's going to represent this area right here, below the x-axis to the function. And when we are above the x-axis, it's going to be from the function to the x-axis right there. This blue area is positive area as we are above the x-axis. And this red area is negative area. And that's what we mean by signed area from f of x to the x-axis, as we can have positive or negative area there. When we're thinking about this limit of the sum, that's our idea that if we have more rectangles, the area of the rectangles is actually equal to the area under the curve as n goes to infinity. So let's look at 3 examples of that. Same example, just 3 times. I'm going to think about just this function right here. We're going to look at this with 3 rectangles and then some more rectangles after that. So the first one, let's say we estimated this with 3 rectangles, this area. The first rectangle would have a negative area, the second 2 would have a positive area, and this would estimate the area under the curve, the signed area from the function to the x-axis. But if I had more rectangles, let's draw some more here, from the x-axis to the function, in this case, I drew 10 rectangles. That is going to be a better estimate of the area. And let's draw even more here. This time my rectangles are going to be very, very skinny. It's just going to be the width of the pencil that I'm drawing with here. In this case, I drew 40 rectangles there. In this case, the rectangle is really just that width. The width here we're going to call delta x. The height of the rectangle is f of x sub I, and we can do that for all of these rectangles here. In this case, the first one, delta x is pretty large. We still have the height of the function at some point. So we can see that if I had more than 40, 100, million, a billion rectangles, this is starting to become very, very close to the actual area. In fact, we're already very, very close with n equals to 40. Right, so this is an idea from the previous section, but now we are just giving a name to it. This is now called the definite integral of the function from a to b. So let's think about some properties of definite integrals. We talked about properties of our limits, of our derivatives, of our indefinite integrals, and now we're going to talk about definite integrals. First one is the integral from a to a of f of x dx is going to be 0. This is saying that the area under the curve from a to a is 0. And since there is no interval there that we are considering, that is really just saying that a and a are the same points, and there's no area to consider there, so it's going to be 0. The next one is just a definition kind of thing. If I flip the bounds, if I go from b to a instead of a to b, then I'm just going to say that is the negative of the integral. So for example, if I have the integral from 2 to 5 of f of x dx, let's even just put a function there, how about like x squared dx, that is equal to negative the integral from 5 to 2 x squared dx. We can just put a negative on there. We are always going to try to write our bounds from least to greatest, the least one on the bottom, the greatest one on the top, but that is something that we can work with there. All right, next one is an important one, and we can understand with the area here. The integral from a to c plus the integral from c to b is just the integral from a to b. We can see that with a quick picture. Let's think about an integral here. We have 3 different x values, a, c, and b, and let's just draw some function, f of x. This is saying that if I want to look at the area under the curve from a to c, the first integral, I am considering this area here. If I want to consider the integral from c to b, that's the area under the curve from c to b, that'll be that area. So if I want to consider the area from a to b, I can just take the area from a to c plus the area from c to b, and that'll give me the whole thing. I can just add 2 smaller areas together. That's one that's pretty intuitive, but it can be useful to write like that. The next one is I can bring a constant out in front of the integral. This idea comes from the idea that we can do that with limits, as this integral is a limit kind of operation. Let's go back one page to see that. The definition of the integral is going to be a limit of a bunch of terms added up. And since I can bring a constant in front of a limit, I am able to bring a constant in front of the integrals for the exact same reason there. We could draw some pictures to convince ourselves of that as well, but we're just going to leave it right there. And that's something that we're going to do a lot of, bring constants in front of integrals. And we'll see an example of that later in this talk. Finally, we have the integral of a to b of 2 functions added together or subtracted. We can think of each of those separately, and this time a picture could be very useful. So let's think about 2 functions here, f of x and g of x on the interval a to b. If I want to consider the integral of f plus g, which is going to be something up here, adding those 2 things together, I can just think about the area of f plus the area of g. Maybe the best way to think about it is with a rectangle here. If this is f plus g of some x value, that's just going to be adding 2 rectangles together, and those 2 rectangles have heights of x sub I and g of x sub I. Note that delta x is not changing. So now let's look at some examples. First one, let's find the integral from -1 to 2 of 2x plus 3 using geometric formulas. The idea here is that we're looking for the area under the curve, and this is going to be given by some nice formula here. So let's draw this function, 2x plus 3, on this interval. So we're going to go from -1 to 2. And 2x plus 3 has a y-intercept of 3. So it has a y-intercept of 3, a slope of 2. And this is going to give us a linear function we can draw right here. And if we're thinking about the area under the curve to the x-axis, we're thinking about a nice shape, a trapezoid that we can find the area of. And maybe the best way to do that is to find the area of this little rectangle first. Plus the area of this triangle. That will give us the area from the function to the x-axis, from -1 to 2. So let's think first of the area of the triangle. That's going to be 1/2 base times height. In this case, the base is 3, and this height is going to be from 1 to 7, so this is 6. This will give us 1/2 3 times 6, which is 9 units squared. Then the area of the rectangle is just base times height. In this case, the height is 1 and the base is 3 that we already saw. So this will give us 3 times 1, 3 units squared. So the area total, which is given by the integral, is equal to 9 plus 3, or 12 units squared. There's another way that we could do this using some rules. So let's think about this. We'll say this is, or we can break up this integral over addition, giving us the integral of 2x plus the integral of 3. Now in this example, it may not be that helpful, but let's just see what would happen here. So from -1 to 2, 2x is an easier function to draw. So 2x here would have a y-intercept of 0. We'll have that function right there. So we're thinking about this area. We would have two areas to compute both those triangles. This area here would be 1/2 2 times 4, which is 4 units squared. This area would be 1/2 2 times 1, or 1 unit squared. And note that this is negative. So the area total is going to be 4 minus 1, which would be 3 units squared. And that's going to be all plus the integral of 3. So that integral from -1 to 2, the constant function 3, is just a straight line. Y equals 3. And this area is easy to compute. This is just going to be 3 times 3 would be 9 units squared, base times height. And again, we would get the same result, 3 plus 9, 12 units squared. Now in this example, I think doing it the first way would be the easiest, but it's another option that we have to deal with integrals. We can break it up into a couple different ideas. All right, let's do the similar kind of thing. This time we have square root of 9 minus x squared from negative 3 to 3. This is not as easy of a function to draw, but we can think about what this function is. So this is the function y equals square root of 9 minus x squared. And if we fidget with this expression, we could write this as y squared equals 9 minus x squared. Or we could say this is x squared plus y squared equals 9. And that is a circle of radius 3. And when we're thinking about this circle, the square root comes from the top half of the circle is the positive part of the square root, and the bottom half of the circle is the negative part of the square root. So when I'm given the function square root of 9 minus x squared, what I am really dealing with is the top half of the circle of a radius 3 centered at the origin. So I'm thinking about this area. I'm thinking about the area from the function to the x-axis. And this area is going to be 1/2 times the area of the circle, pi r squared, 1/2 pi times 3 squared will give us 9 pi over 2 units squared. So although this may not have looked like a very nice function to deal with at the beginning, this is a circle, and that is a very nice function. We have nice formulas for that. All right, so a different kind of problem. This time we're given the picture of the function, and we need to find the area. So the first thing we need to do is sketch the area that we are dealing with. We're going from negative 3 to 4. So here's negative 3. Here's 4. We're thinking about the area from the function to the x-axis. So let's sketch that area. We're going to have different parts of the function that we're going to deal with, and I'm going to break those up into different colors. So they're nice shapes. So again, from the function down to the x-axis. And the last chunk here is definitely the weirdest part. We have that. So let's think about these areas. First one is going to have, it's going to be negative. Okay, it's below the x-axis. Negative 1/2 base times height. Negative 1/2 1 times 1, which is negative 1/2. The green area here is going to be 1/2 base times height, 1/2 times, and hold on a second. I made a mistake with these values here. I was being a little bit cavalier. I was off on what these values actually are. To make this easy, I wanted this to be the value -2 right there, which means that my areas are correct. Sorry about that. So this time the base would be 2, the height would be 2, this would be an area of positive 2. For the square here, it's going to be just base times height, so that's going to be 2 times 2. For the triangle, it's going to be 1/2 base 1 times height 2, give us an area of 1. And then the more difficult one to deal with is this weird circular kind of shape. But it might be useful to think about this as a square minus a circle. And not really a circle, but 1/4 of a circle. And if we think about it that way, that will give us the square is going to be an area of 2 times 2. And then the circle is going to be minus 1/4 pi r squared. In this case, r is 2, where that center give us the where that square meets up. So this will give us an area of 4 minus 1/4 pi 2 squared, which will give us 4 minus pi. So the area total given by this function is going to be negative 1/2 plus 2 plus 4 plus 1 plus 4 minus pi, which will give us 11 minus 1/2 minus pi. We could write that as 21/2 minus pi. I think that's how we'll write it, units squared. The idea is that we can break up this picture into a lot of different chunks that have nice shapes, and we can deal with those, remembering that it's negative area below the x-axis. All right, another kind of problem we can deal with is if we're given some values of the integral. So in this case, we know that the integral from 1 to 2 of x squared is 7/3. The integral from 1 to 2 of x is 3/2. And the integral from 1 to 2 of 1. And it's important to know that this is a hidden kind of function of 1 is 1. Then we can deal with something a little more complicated, like the integral of negative 3x squared plus 4x minus 5, using some rules that we have before. This integral is going to be equal to, we can break this up over additions. This is the integral of negative 3x squared plus the integral of 4x plus the integral of negative 5, or minus that integral, and we can bring out a constant in front of all of those. We have negative 3 times the integral of x squared plus 4 times the integral of x minus 5, the integral of 1. And we know what those values are. So this is a value of 7/3. This has a value of 3/2. And this has a value of 1. So plugging those numbers in, we have negative 3 times 7/3 plus 4 times 3/2 minus 5 times 1 will give us a negative 7 plus 6 minus 5 would give us a negative 6. And we're thinking about area, so this is units squared. We're going to think about in the next section, how do we come up with these values of 7/3, 3/2, and 1? There's going to be a nice way that we can do this, but at this moment, if we're given those values, we can come up with more complicated functions as well. All right, one more example we can deal with in this section, and that is something like find the integral of 0 to 6 of 1/3 y dy. In this case, having the y's there makes a difference. So this is going to be represent the signed area from the function f of y to the y-axis. And let's think about what that means. So this function 1/3 y we could write as 3x equals y. That's a function of x. We could sketch that function. It has a y-intercept of 0. It's going to go through these 2 points here. So this is the function x equals 1/3 y. Now when we're talking about this integral, since this is in terms of y, this is not x values that represent the bounds, but y values. And this is in corresponding to these y values here, a y value of 0, y value of 6. That's our bounds of our integral. And if you could just turn the paper 90 degrees, you can kind of see this would be very similar to our problems we did before. But the area we're looking for here is the area from the function to the y-axis. And that area would be 1/2 2 times 6, or 6 units squared. Just noting that when we do it in terms of y, we are talking about a different kind of area. Going back to a couple sections ago, we can think about this, or sorry, the last section. We can think about this with rectangles. That's where all this is coming from, and we could estimate this area with a bunch of rectangles. In this case, the rectangles are horizontal rectangles. The width of those is going to be f of y sub I for some y, and the height is going to be some delta y. So in the next section, we're going to learn how do we actually come up with the values of more complicated integrals quickly. And we're going to be using the antiderivative of the function to do that. We talked about that in section 4.1, and we're going to merge the ideas of indefinite and definite integrals together to be able to solve definite integrals easily with the fundamental theorem of calculus.